Today we will learn about the signal correlator, actually the correlator demodulator. Correlator demodulator is the name as it is the name is given. It is used in the demodulation process. So we have a correlator demodulator at the receiving end. So we will in today's topic we will revise some basics of the process of correlation. Then we will see we will choose two signals for data transmission, S0 of t and S1 of t. We will choose two signals for binary data transmission. So we expect that our data bits are some binary sequence. Our data bits is a binary sequence, and we represent a binary 1 and a binary 0 by two waveforms, that is S0 of t and S1 of t. So we would choose two signals, and then we will see that when we transmit any of these two signals, what would be our received signal. Well, here we would discuss our received signal, our received noisy signal in the presence of white noise only. So our received signal R of t, the expression of received signal would be only in the presence of white Gaussian noise. So we expect that the channel is ideal, and we have, or in other words, we have only AWGN channel, that is additive white Gaussian noise is present. AWGN channel, our signal passes through AWGN channel. So we would see the expression, mathematical expression for R of t. Then we would discuss the signal correlator, at block level. So the block diagram of signal correlator would be discussed, and finally we would observe the output of our correlator for these signals S0 of t and S1 of t. So we would see the output of our correlator. So let's move to the process of correlation first. We would discuss the correlation as we have covered this topic earlier, but let me recall it for the purpose of understanding today's topic. Suppose we have a pulse which is from 0 to TB. It's a bit interval, it's a time axis, and you have this, suppose you have x of t. This is a time domain function. If you want to find the correlation, the autocorrelation, suppose we are interested in the autocorrelation. So as you know, we define the autocorrelation function by this expression R of tau, which is from minus infinity to plus infinity. We can say x of t t minus tau, right? T minus tau d dt. So this is the expression for our the autocorrelation function. So we already know this function, autocorrelation function. Actually, what does this expression explains? If you see, if you closely observe your expression, it is actually the product of x of t with its shifted version. So we are integrating this product. Of course, I can put limits over here. I can just write, instead of minus infinity plus infinity, we can just write our limits. So we can say our signal exists only from 0 to capital T, right? So we can just put these limits, and to be very accurate, we can always divide it by the time interval, right? Just to normalize it. So this is the expression. This is the expression for correlation. Now, if we are interested in finding out the autocorrelation of this function, how it would look like, so let me draw the correlation function. So if you observe your pulse, it is this waveform. We have a time domain pulse which exists from 0 to, let me simplify it, let me give it a period unity 1, 0 to 1, right? And let me further simplify it here by giving its amplitude plus 1. So we have an x of t which exists between 0 to 1, and it has the peak amplitude, which is plus 1. If I want to find the autocorrelation function, autocorrelation of this function with the same pulse, right? Autocorrelation is the correlation with this shifted version of the same pulse. So this is the shifted. Now I will shift this pulse. I will shift the one shown in the black color, and we would like to draw our autocorrelation function. We would like to draw our final function in over here, right? So let me draw this function here. Now there is no shift. If you see these two waveforms, no shift right now. So our r of tau is from the above expression. If you see, our r of tau is, as I said earlier, our r of tau is just to if we plug these values, it from 0 to 1, right? It's from 0 to 1, 0 to 1, the time interval. Then I have x of t, and the product with x t minus tau dt. We have to find out this integral, the result of this integral. Now when there is no shift, tau is equal to 0, right? This tau variable is 0 for the first value. I am taking tau is 0. When tau is 0, actually we have x of t multiplied with x of t. So x of t multiplied with x of t when tau is 0. Actually it's the square. We are integrating the square of a signal over the period 0 to 1. Now we have tau 0. So keep this in mind. We have tau 0, and we are trying to integrate this curve. Now okay, we have the, now this is the definite integral. Keep in mind, this r of tau is a definite integral, which means it will give us some number, some value. It would give us some number now, because the integral is over the period. So it's for a fixed period 0 to 1, or a fixed period 0 to 1. So it would give us some number. It would give us some number which we have to plot, and the value of that number would depend upon this variable tau. Now when tau is 0, it is actually the product of the x of t with x of t, and if we find this product, we have this is 1, and this is also 1, right? From 0 to 1, from 0 to 1. So both the values R1. So we would get exactly, we would get 1 multiplied by 1 is 1. If you integrate it from 0 to 1, you would get 1. So here at this is the tau axis. Now we have the tau axis. Here the first value which we get is unity, which is 1, right? This is 1, the first value. Now for the second value, you can choose any value of tau, this variable tau. Just have a shift. So let me say this tau is positive. Suppose this is positive and it is 1 by 4. I can take 1 by 4, which is just it means our signal. Now let me if the tau is 1 by 4, what does it mean? It means that we have to multiply x of t with x of t minus 1 over 4, which is the delayed version of this signal. So let me draw that delayed version. Let me draw that delayed version. So if I draw the delayed version of the signal by 1 by 4, this is half, right? So 1 by 4 would be a delayed version which starts from somewhere here and up to here, right? This is the period 1. Now if we multiply, now again we have to find this product. So if we multiply this waveform with the blue waveform with the black one, we would get the multiplication result only in this area, because here onward this function is 0. So 0 multiplied with this part, it has 1, but here it is 0, so we would get 0. So we would get the result only, the multiplication result only for this one, this area. This is here it is 1, and that is also 1. So we have from the, now the integral limit, you can see it is from 1 over 4 up to 1. So our limits, which is from 0 to 1, effectively it is from 1 over 4 up to 1. So if you integrate, now let me do it here for explanation. Now your r of tau, if you observe your r of tau, it is from effectively from 1 over 4 up to 1. X of t is unity, and this is also unity dt, and if you solve it, you will get 1 minus 1 over 4, which is 3 over 4. So your next point, which is taken here at 1 over 4, is actually 3 over 4, right? Which should be somewhere here, just approximately it would be here. Now you can plot it for 1 over 2, right? And if you observe your signal for 1 over 2, now you can plot your signal for 1 over 2, and if you see it further, it will move further. Now when tau is, we got 2 points right now. You can observe we got 2 points. One point is here, which at 0. One point is at 0, which is 1. The other point is at 3 by 4. The other point is at tau 3 by 4, which is 3 over 4. Now if we get another tau value, which suppose it is 2 half. Suppose tau is half. So this waveform further moves there, here, just this red one. So we have shifted it further, and now the product value will be, I'll mark it red. Now you can see we have a product only this part, because here we have the function is 1 and here also it is 1. So it's actually the limit of the integration is from half to 1. So the limit is from half to 1, right? Now if you integrate it, you would get half. You would get another point which is half. Similarly, if you further move it to sorry, this was 1 by 4, right? This one was 3 by 4. This was at 1 by 4, then half, then 3 by 4. When you see at 3 by 4, you would get a value which is 1 over 4, and at a value 1, when you check it at 1, you would get because your waveform, when tau is 1, your waveform is here. It starts from here and it goes up to here, right? This green waveform. So there is no overlap at tau equal to 1, and you would get 0. You would get 0. Now if you join these points, this is your autocorrelation for positive values of tau. Similarly, you can repeat it for negative value of tau, and for negative value of tau you would get these values. At -1 there will be no overlap, and your autocorrelation function looks like this for this pulse. It looks like this, right? Which is an even function of tau. Autocorrelation is an even function of tau. We discussed this theory earlier. Now we would because we are taking, we will see that our correlator actually correlates the received signal with the existing replicas. So this process is important to recall. Now let me briefly give you the idea. But actually our next step is to choose two waveforms. So we would choose two waveforms, and those two S0 of t and S1 of t. We would choose two waveforms, S0 of t and S1 of t, for transmission of binary data. Well, the objective of Correlator Demodulator is to successfully detect the signals buried in white noise by matching process, right? So it would detect the signal. It would successfully detect the signals which are buried in white noise by the process of matching or comparison. So actually we would see that our signals, suppose we are because we are assuming that data is binary, and we are selecting these two waveforms for transmission of this binary data. So we have these two waveforms, and the waveforms look like this. So our two waveforms are S0 of t. The two waveforms are S0 of t, which is a pulse from 0 to TB, the bit interval, and it has a magnitude A plus A. Similarly, we have another waveform which is from 0 to TB, but it is like this. It is like this, right? So it is this waveform which has a plus A and a minus A amplitude from 0 to TB. Here this interval is TB. This also is from 0 to TB. So we have S1 of t, S0 of t and S1 of t, two waveforms. And if you closely observe these waveforms, these are orthogonal. You can see these waveforms are the waveforms which we have selected are orthogonal. So orthogonal signals are used for transmission because they have the correlation. They S0 and S1, if you observe the correlation of S0 and S1, it is 0. So they are like complete strangers. They are like complete strangers for each other, S0 of t and S1 of t. So the correlation means they have no similarity, and you can verify it. Just try to find out the product and integrate it over this period, and you would see that it turns out to be 0. So these waveforms are orthogonal. The property of these waveforms, they are orthogonal. So these S0 and S1 are orthogonal, which means that if you try to find out the correlation, S0 of t and cross correlation, we say S0 of t and S1 of t, and you integrate it over the this integral, you can see that it is clear from this these figures that in this given period you would observe that this is your r of 0, right? So you can clearly observe that from you can just break it into two integrals from 0 to half, or not half, let me tb over 2. The period is tv, not 1, right? You generalize tv, so that it from 0 to tb over 2. tb over 2, your S0 is 1 and S1 is also 1, a dt, plus from tb over 2 up to capital TB, your signal is S0 is 1 and this one is minus 1 dt. So if you integrate it, if you solve this integral, you would see that here you have t sub b over 2, and from this integral you would get minus what do you get? Minus t minus t sub b over 2. From here you would get minus t sub b over 2, and actually it is 0. So you can verify that these two waveforms are orthogonal. We would use these two waveforms for transmission of binary data, and we would see that our signal at the receiving end, which is r of t, its expression is given by r of t is equal to si of t plus n of t. So this is the expression for our received signal. And what is this I? I is either 0 or 1, right? So it means that our received signal is either S0 of t plus n of t, or it is S1 of t plus n of t. So your signal is either it is S0 of t plus n of t. Keep in mind this is for t in between this interval 0 to tb, right? Either it is this one, or your received signal is S1 of t plus n of t in this period. Now the detector has to detect whether the received signal is S0 plus noise or it is S1 plus noise. This will be detected by the the process of correlation. So the simplest way is to correlate the signal R of t with S naught of t. To find out the correlation of R of t with S naught of t, suppose that correlation give us some value which I say R. Suppose that value is R naught, and we also try to find out the correlation of R of t with S1 of t, right? R of t with S1 of t, and that correlation give us a value R1. Now based on this one, this R1 and R0 and R1, based on this R0 and R1, detector would decide whether the signal is S0 or the signal is S1. So if R0 is greater, if R0 is greater than R1, because we are comparing R of t with S0 and S1, right? We are comparing it with both. If we get this result, it means R0, the higher value of R0 means that it is more like S0. However, if R1 is greater than R0, it means that the received signal is more like S1. So based on these values of R0 and R1, our detector take decision in favor of S0 and S1. So this is how the detector has to take decision. Now let me draw the circuit diagram for the block, the circuit diagram for our correlator demodulator, how it would look like. If you observe your correlator demodulator, it looks like at a block level we can say that okay, our received signal, we have a received signal R of t, and we would like to, because we want the correlation, so we would like to multiply S naught of t with our received signal, right? And then we would integrate it. We would integrate that signal, that product, and the integral, the value of the integral taken, this integral continuously give you the output, but we would choose the output which is at time instant tb, why we choose this value? Because this is the we will see that this value is important, this instant is important, t is equal to tb instant is important, and the reason is when t is equal to tb you get the correlation, the maximum correlation at t equal to tb, you get the maximum correlation. So you can observe it, from the you will see it in a short while. The maximum correlation would be at t equal to tb. Similarly, in the lower branch, now this upper branch gives us the correlation, the result of this upper branch gives us a number R0 which represents the correlation of received signal with S0, right? This number represents the correlation of R of t with S0 of t. Now, in the we need another branch because we have orthogonal signals, so we need another branch, the lower branch. And in the lower branch, what we would do, we would multiply. We would multiply S1 of t with the received signal, and we would like to integrate. We would like to integrate this product, and we would observe the value of this integrator. We would observe the value of this integrator R1 at t equal to tv, the same instant, right? The same instant we would observe this value, and this number R1, this would represent the similarity. This would represent, this is actually the measure of a similarity of received signal with S1 of t. So R naught of t is the measure of similarity of received signal with S naught of t, and R1 of t is the measure of similarity of the received signal with S1 of t. So we will continue here. We will continue the signal correlator in the next video lecture.